Welcome to This Explainer. Today, we're unpacking the awe-inspiring mechanics behind nature's most magnificent and, let's be real, destructive engines, Pacific hurricanes. And we're going to use the life cycle of a single, fascinating system, Hurricane Fausto, as our guide to understanding the broader science. So, let's dive right into this, because the journey of a hurricane is honestly one of the most incredible physical processes on our planet.
To understand a storm like Fausto, we really have to start at the source. We're talking 63 million square miles of silent, stored energy. The Pacific is the largest and deepest ocean on Earth. Every single second, the tropical sun is just pouring unimaginable amounts of heat into this water. And unlike land, water absorbs heat slowly, but it also releases it slowly. This effectively turns the entire Pacific Ocean into a giant natural battery. Most days, this energy simply warms the water and drives invisible ocean currents. But occasionally, the atmosphere taps directly into this immense reservoir.
And that brings us to the core mystery we're exploring today. How exactly does a scattered cluster of totally ordinary, everyday thunderstorms manage to organize into a monstrous heat engine like Hurricane Fausto? It's a question that has driven meteorologists for decades. Because thousands of thunderstorms form over the Pacific every day, release their rain, and then just vanish. But for a hurricane to ignite, the atmosphere requires an astonishingly precise alignment of forces.
Section 1. Birth of a hurricane. The precise recipe. So, tropical cyclones are actually incredibly fragile in their infancy, and they require immense heat energy to fuel their engine. The critical threshold here is 26.5 degrees Celsius, or right around 80 degrees Fahrenheit. This is the baseline sea surface temperature needed to provide that high-octane fuel. But actually, temperature alone at the surface isn't enough. That warmth must extend deep beneath the waves. As a developing storm's winds churn up the water, it needs to continually pull up warm fuel. If there's cold water sitting just below the surface, the engine completely stalls out.
So, the crucial point here is that a hurricane needs a complete 5-part recipe. First, we have warm ocean water. Second, abundant moisture. As water evaporates, it stores energy. When that vapor condenses into clouds, it releases that stored energy, which we call latent heat, and that forces the air to rise even faster. Third, you absolutely need low atmospheric pressure at the surface to draw that air inward. Fourth is the Coriolis effect, Earth's rotation, which causes that inrushing air to curve and spin. That is exactly why hurricanes don't form directly on the equator, by the way. And fifth, we need low vertical wind shear. If winds at the top of the atmosphere are blowing in a completely different direction than winds at the bottom, it will literally push the storm over and tear it apart. If even one of these 5 ingredients is missing, the whole shebang just falls apart.
Section 2. The Pacific's giant engine, balancing the ocean. Now, zooming out a bit, the Pacific is this grand balancing act, heavily governed by the El Niño and La Niña climate cycles. During El Niño, trade winds weaken and unusually warm water spreads across the eastern Pacific. This basically charges our ocean battery, creating a highly favorable environment for storms like Fausto to thrive. Conversely, La Niña brings stronger trade winds and pulls cooler water up from the deep, a process called upwelling, which essentially drains the battery and suppresses hurricane development in the eastern Pacific. Nature is just constantly shifting this balance of power.
Section 3. Hawaii's invisible shield, an isolated anomaly.
So if the Pacific is a giant hurricane factory, why does Hawaii, a highly exposed island chain sitting right in the middle of it, so rarely take a direct hit? Well, it's not luck, it's physics. Hawaii is surrounded by a stacked natural defense system. First, as storms move westward toward the islands, they very often encounter patches of cooler surrounding waters, instantly choking off their fuel supply. Second, they frequently run into a wall of high vertical wind shear, which, as we just learned, tilts and destabilizes the hurricane structure. Add to that intruding dry air that literally starves the storm of moisture, and Hawaii's famous steady trade winds that disrupt the storm's environment. These natural defense mechanisms act together to systematically tear apart the structure of an approaching hurricane.
Section 4. Predicting the unpredictable, the tech array. Okay, this number is just staggering, 22,000 miles. That is the altitude of our geostationary weather satellites. By orbiting at the exact same speed that the Earth rotates, these satellites serve as our permanent, unblinking cameras in the sky. They use visible light during the day, infrared at night to measure cloud top temperatures, and even microwave sensors that can peer directly through thick clouds to reveal a storm's hidden circulation. They're tracking hurricanes day and night long before they ever approach land. But satellites can only see so much from space. Sometimes we literally have to fly directly into the monster. The hurricane hunters deliberately fly specialized aircraft into the absolute most violent part of the storm, the eye wall. And why do they do this? To deploy a drop sonde. This instrument falls through the storm on a parachute, transmitting real-time data on pressure, temperature, humidity, and wind speed directly back to the plane. It gathers critical internal data that satellites simply cannot see from orbit. It's wild stuff.
So what happens to all this data? Everything from satellites, drop-ons, and ocean buoys gets fed into some of the world's most powerful supercomputers. Because the atmosphere is incredibly chaotic, right? A tiny difference in initial data can drastically change a forecast. So meteorologists rely on ensemble forecasts. Instead of running just one simulation, they run dozens, each with slightly different starting conditions, to find agreement on a hurricane's most probable future track.
And now we're entering a totally new era. Artificial intelligence is stepping in to find the hidden patterns in the atmosphere. AI systems can rapidly analyze massive historical data sets to spot really subtle signals that human forecasters might easily miss. This is absolutely crucial for predicting rapid intensification, which is when a storm's winds just suddenly explode in strength. It's one of the hardest things to forecast, and AI is fast becoming a vital tool in cracking that code.
Section 5. The future of storms. Decades of data. Now, looking at the big picture, there is a physical chain reaction taking place, and it's grounded in strict thermodynamic science. Step 1. Our oceans have absorbed the vast majority of excess heat in recent decades. Step 2. Warmer ocean water increases evaporation. Step 3. A warmer atmosphere can hold way more of that moisture. And step 4. Because moisture is the latent heat that fuels a hurricane, storms moving through these environments can produce much heavier rainfall and reach higher peak intensities. It is a direct, verified chain of cause and effect.
But the nuance here is critical. The science doesn't necessarily say we're seeing more hurricanes overall. Actually, scratch that. It's more like a larger proportion of the storms that do form are reaching Category 3, 4, and 5 status. We are definitely seeing a shift toward major, catastrophic intensities when the environmental conditions align. And that leads to a crucial takeaway for all of us. When we think of hurricanes, we usually picture destructive wind, right? But the greatest threat is actually water. Because of heavier rainfall capabilities and rising sea levels, storm surge reaches much further inland than it used to. To put that into perspective, water, not wind, now poses the most severe and devastating danger to our coastal infrastructure and communities.
The life cycle of Hurricane Fausto teaches us so much, but it ultimately brings us back to this one thought. The more we understand our planet, the better prepared we become to live with its power. Technology is incredible, no doubt about it, but forecasts only save lives when communities trust them, prepare for them, and truly respect the sheer power of the oceans. Scientific collaboration and human preparedness are for sure our very best defenses against nature.
Fastest clouds have faded, its winds have died down, but the Pacific Ocean remains. The warm currents keep flowing, and the atmosphere keeps churning. So I want to leave you with this final thought to ponder. As our planet's climate continues to evolve and our technologies grow ever more advanced, what exactly will the atmosphere write in its next chapter? Thank you so much for joining me for this explainer. Keep exploring and stay curious.